Friends, welcome to my YouTube channel Easy Mathematics. On our last video lecture, we come to know about chromatic polynomial. In this video lecture, we discuss some theorems on chromatic polynomial. So the first theorem is prove that chromatic polynomial is a polynomial in lambda. So chromatic polynomial, we are saying it always a polynomial. So it is really a polynomial or not, that we discuss in this theorem. So how to prove it? Let Pn lambda yields the number of ways of properly coloring of G with n vertices using lambda or fewer colors. So initially a graph G is given with n number of vertices and we should choose lambda different colors to color the graph G. Definitely lambda value should be less than or equals to n, the number of vertices. Now out of this lambda, if we choose any color means any I number of colors to color the graph, suppose properly. That means if we choose I different colors from the lambda colors to color the graph properly, then there are definitely Ci different ways are there. From the lambda, if we select I different colors and if it is possible to color the graph properly by using I different colors, then by using I different colors out of lambda, there are let Ci be the different ways of properly color that graph G. Again, these I colors can be selected from lambda different colors. Total lambda number of colors are there. From there we have chosen the I different colors. I may be 1, 2, 3, 4, anything up to lambda. It definitely not be 0 because a graph coloring means at least one color we should require. So now if I colors can be selected from lambda different colors from the selected colors lambda, then there are definitely lambda Ci ways. Out of lambda, if I colors be taken, then there is possibility of different number of ways of choosing I such colors are lambda Ci. And using this I colors, if we color the graph properly, then this different coloring can be possible by Ci different number of ways. So the total number of coloring, that means the way of coloring of a graph using I colors is Ci into lambda Ci ways. So hence the total number of colors, the total number of ways of properly coloring of G using exactly I colors from lambda or fewer color is this one. When I is equals to 1, then it should be Ci lambda C1. When I is equals to 2, then it is C2 lambda C2. In this way, we will find out the different number of ways to color by choosing 1, 2, 3, 4. In this way up to lambda number of colors, and finally if we add all of them, then we will find out the total number of way by which we can color the given graph using the lambda different colors, so that we can find out this one where this lambda Ci we know from the binomial, this one is lambda into lambda minus 1 into lambda minus 2. In this way it is up to lambda minus I plus 1 divided by factorial of I. So if we sum up this one and finally we expand this one, then definitely we will find out it is a polynomial in lambda. Hence the proof. Next theorem is prove that the chromatic polynomial of a complete graph with n vertices is Pn lambda is equals to lambda into lambda minus 1 into lambda minus 2. In this way it is up to lambda minus n plus 1, where n is the number of vertices. So what is the second theorem? The proof that the chromatic polynomial of a complete graph with n vertices is this one. So now how to prove this one? Initially the given graph is a complete graph. So let Kn be the graph which is a complete graph with n number of vertices. So since Kn is complete, therefore it contains exactly one edge between each pair of distinct vertices. So with lambda colors, there are lambda different ways of coloring any selected vertex of a graph. So a second vertex can be colored. So a second vertex can be colored properly in exactly lambda minus 1 ways. Total n number of vertices are there, lambda number of colors we have chosen. So the first vertex can be colored in the lambda different ways, because out of lambda we can choose any color in lambda ways. After choosing the one particular color from lambda, then the second vertex can be chosen in lambda minus 1 different ways. Then the third vertex similarly can be chosen in lambda minus 2 ways, and the fourth vertex is lambda minus 3 ways, and so on. So all the vertices we can choose in this way. Then for each vertex we will sum up that for first vertex it is lambda, for second it is lambda minus 1, for third it is lambda minus 2. In this way it is up to nth vertex, it should be lambda into lambda minus of n plus of. Finally, the nth vertex can be properly colored in lambda minus n plus 1 ways. So by principle of counting, the graph Kn can be colored in lambda into lambda minus 1 into lambda minus 2, in this way up to lambda minus n plus 1 ways. Thus, this one is the chromatic polynomial for a graph which is a complete graph with n number of vertices. Hence the proof. Next, the third theorem, and the third theorem is prove that the chromatic polynomial of null graph G with n vertices is lambda to the power of n. So a null graph means that any number of vertex you might have, but no edges should be there. So that if n number of vertices are there, so we consider a graph G with n vertices. So since no vertex in null graph G is adjacent to any other vertex, therefore each of them can be colored independently by using lambda different colors in lambda to the power n ways, as each vertex can be colored by lambda ways and there are n such vertices. If it is a null graph, so null graph means only the vertices are there. So any vertex if we color, so total lambda number of colors are there, then we can choose any one color from out of this lambda. So there are total lambda ways to choose the first color. Again, for this one, as these are not adjacent vertices, that's why again we can choose lambda different colors for coloring this vertex again. For this one, again these are not adjacent to any other, so that lambda number of colors again we can consider for this one again. Similarly, whatever be the vertices are given in a null graph, for each and every vertex we can choose lambda different ways or lambda different colors from the lambda different colors, so that we can say for each vertex the total number of ways by which we can choose a color is lambda. Hence, depending upon the total number of vertices, the polynomial should be then lambda to the power n. That is by the principle of counting we will find out. Hence the proof. Now one more theorem in this video. So that theorem is, here it is the fourth theorem. So prove that the chromatic polynomial of a tree with n vertices is lambda into lambda minus 1 to the power n minus 1. This theorem, if we want to prove, then we use the mathematical induction method. So what we will do, at first we will consider that let T be a tree with n number of vertices. So initially given graph is a tree, so let us consider a graph is T, which is a tree with n number of vertices. So this one we are going to prove by the mathematical induction. So initially let n is equals to 1. The number of vertices are given in the tree is 1. Then it can be colored by lambda different ways using the lambda colors. So that from the theorem we can write it is lambda into lambda minus 1 to the power 1 minus 1. As we consider n is equals to 1 by the mathematical induction, we just substitute the value n for 1. So that we will find out this value is lambda, which is the lambda different colors to color the one vertex which we have in the tree. So that this one proves that for n is equals to 1, the theorem is true. Hence, the given statement is true for n is equals to 1, we can see. Now suppose that this theorem is true for m. That means when n is equals to m, then the theorem is true. Hence, we can assume, or we can have that Pm lambda is equals to lambda into lambda minus 1 to the power m minus 1 by the mathematical induction. Now we have to prove that the tree or that the theorem is true for n is equals to m plus 1. So the number of vertices now it is m plus 1. So what we will do, initially with the tree where the tree having the m plus 1 number of vertices, we should delete one vertex, one pendant vertex from this tree. That means from this tree where the total number of vertices are m plus 1. So after that deletion, what happens? The tree will contain total m number of vertices. We have started from the m plus 1 number of vertices. Now if we delete one vertex, then what will happen? The tree will have total m number of vertices. We will delete one pendant vertex there. So if we give an example here, or just a pictorial notation, then this one is a tree. Suppose it having the m plus 1 total vertices, and these are the two vertices we consider. One is u and one is v. Now we delete this vertex v. So then what happens? The remaining tree having the total m number of vertices, and after removal of this one, this edge also be removed. So that what we will find out, after deletion of one pendant vertex v from T, it contains m vertices, and this tree T minus v, the chromatic polynomial should be this one, lambda of lambda minus 1 to the power m minus 1. So this is by induction hypothesis. Since v is the pendant vertex of T, it is adjacent to only one vertex, say u. That means as v is the pendant vertex, then it is obvious that it is the adjacent to exactly one vertex. So therefore v can be assigned with any of lambda minus 1 colors. Tree means no cycles are there, so whatever be the colors lambda are there, if we have, then to color this v, definitely except this color, we can choose any other colors for the previous one. So total lambda minus 1 different colors are required. So by principle of counting, the chromatic polynomial of T will be what then? For v, we should include lambda minus 1 with the polynomial lambda of lambda minus 1 to the power m minus 1. So it is lambda minus 1 into lambda minus 1 to the power m minus 1. Which will imply lambda into lambda minus 1 to the power of, here we just add m minus 1 plus 1. So that it is finally, we will find out lambda into lambda minus 1 to the power of m. This shows that the theorem is true for n is equals to m plus 1. So this is the proof. So by mathematical induction, we can say that it is true for any n. So that we can say that the chromatic polynomial for a tree is lambda into lambda minus 1 to the power n minus 1 for all n. N is the total number of vertices. So these are the few theorems for the chromatic polynomial. In the next video lecture, we will discuss 2 more theorems and few problems that we will consider in the next video lecture. So thanks for now. Have a nice day.